how's your day going? Today on HaiAstro, we'll talk about the topic, is there one all-powerful superforce controlling the universe? Let's tune in together. Our picture of the universe is something like an elaborate house of cards stacked high on a framework of earlier ideas, approximations, and results that were once tentative and uncertain. Because of this, most experiments in modern theoretical cosmology are very different from those of physics' early days. They are rarely blind expeditions into the unknown. Instead, they are carefully engineered tests designed to confirm predictions that already exist, outcomes that theory has been quietly pointing toward for years or even decades. The Higgs boson is a perfect example. First proposed in 1964, it was finally detected in 2013, almost exactly as theorists had expected. Yet what physicists secretly hope for is not confirmation, but surprise, a result that knocks the whole structure over, forcing us to rebuild it from the ground up, or else locks every piece firmly into place and proves the theory beyond all doubt. And so, in early 2021, inside a laboratory just outside Chicago, nearly 100 scientists who were virtually gathered together collectively held their breath. What they were about to see had the potential to do exactly that. This moment represented the culmination of more than 60 years of work, drawing together physicists from 35 institutions across 7 countries. Yet until a sealed envelope was opened in Batavia, Illinois, and a closely guarded code was entered into a computer, none of them truly knew what they had found. This cloak-and-dagger style of experimental physics, more fitting for a Hollywood thriller than a research lab, was essential. It prevented any of the hundreds of collaborators from unintentionally nudging the analysis toward a result they wanted to see. The experiment underway at Fermilab focused on a peculiar particle known as the muon. Muons are heavier cousins of electrons, unstable entities that exist for just a few microseconds before decaying into lighter particles, often electrons. Like electrons, muons carry electric charge and behave like tiny spinning magnets. When they move through a magnetic field, that spin doesn't stay perfectly aligned, it wobbles. Using the formidable mathematics of quantum mechanics and the framework known as the Standard Model of particle physics, scientists can predict exactly how much that wobble should be. This prediction represents the total of what we believe we know about the universe. The Fermilab experiment was designed to test whether that belief holds up under scrutiny. To carry this out, researchers spent 4 years assembling and calibrating a massive C-shaped magnet, roughly 15 meters across, engineered to produce an extraordinarily uniform magnetic field. For over a year, they circulated muons around this ring and measured their wobble with exquisite precision. While waiting for the muon beam to fire, the scientists overseeing the machine had plenty of time to reflect on the theoretical house of cards beneath their work. Everything in the universe, from the muons racing inside the magnet to the scientists monitoring the instruments, is governed by 4 fundamental, irreducible forces. Gravity keeps a researcher anchored to her chair, pins the magnet to Earth, and holds the planet in its orbit around the Sun. Electromagnetism is responsible for the magnetic field inside the apparatus, but it also does far more. It drives the electrical currents flowing through the control systems and the electrical impulses firing through the scientist's nervous system, keeping her heart beating and her thoughts alive. Zooming further inward down to the atomic scale, the strong nuclear force binds particles together inside every atomic nucleus. It holds protons and neutrons tightly despite their mutual electrical repulsion. Without it, no atoms could exist, not in the lab, not in the scientist's body, not anywhere in the cosmos. Matter itself would dissolve into a cloud of unbound quarks. Yet even now, inside a tiny fraction of the atoms in her body, the weak nuclear force is at work. This 4th force governs radioactive decay, splitting nuclei like potassium-40 inside ourselves and transforming them into something new. Together, gravity, electromagnetism, and the strong and weak nuclear forces appear sufficient to describe every phenomenon we observe in the universe, with one troubling exception. The revelation inside Fermilab's envelope was that the muon wobble predicted by these four forces was wrong. Muons wobble more than they should. With unprecedented precision, the results suggested that something else may be influencing them, perhaps an unknown interaction, a fifth force not accounted for in our models. There is still much work ahead to understand how significant this anomaly truly is, but it already forces us to re-examine what we think we know about the fundamental forces themselves. These forces are the product of centuries of scientific discovery, yet we still don't know why they exist, why they have the strengths they do, or whether they are truly distinct. To explore that, we must extend our house of cards backward to the birth of the universe itself, to a fleeting moment when the forces we now treat as separate were once unified. Humanity has sensed the presence of invisible forces shaping the world for thousands of years, and for nearly as long we have tried to understand and harness them. Naturally magnetic lodestones were prized in ancient China as early as the 2nd century and used in divination. In Egypt, people learned to fear the shocks delivered by electric fish. Early philosophers experimented with static electricity, rubbing amber with fur and marveling at the strange attractions that followed. These effects remained curiosities until the scientific revolution of the 17th and 18th centuries forced nature to give up its secrets. Invisible forces became subjects of serious study, pursued by scholars and statesmen alike. Benjamin Franklin, one of the founding fathers of the United States, is said to have sold many of his possessions to fund his work on electricity. Ironically, his most famous experiment required little more than a kite, a key, and a thunderstorm to demonstrate that lightning was electrical in nature. In the summer of 1864, London was locked in a stifling heat wave. In the wood-paneled offices of King's College, the air hung heavy as James Clerk Maxwell staggered to a window and pushed it open, letting in the noise of the streets below. The air carried a sharp, sweet scent, ozone, a smell Maxwell recognized as the warning of an approaching lightning storm. Eager to finish his work before the sky erupted, Maxwell returned to his desk. For the last time that day, he poured water from a pitcher, creating a steady stream. Rubbing a glass rod against his woolen waistcoat, he held it near the falling water. As expected, the stream bent toward the rod, drawn by an unseen pull. This subtle deflection, magical as it appeared, was static electricity at work, the attraction between electric charges in the rod and the water. Maxwell understood electromagnetism more deeply than anyone of his time. A child prodigy who had spent his teenage years absorbed in mathematics, he now applied that brilliance to the nature of reality itself. Building on centuries of knowledge, Maxwell became the first to visualize non-contact forces as invisible fields, three-dimensional webs radiating outward from their sources. He realized that electricity and magnetism were not separate phenomena at all, but two faces of a single electromagnetic field. When waves ripple through this field, they carry energy without loss. Visible light is one such electromagnetic wave. By uniting electricity, magnetism, and optics, Maxwell transformed physics. His equations laid a cornerstone in our cosmological house of cards, enabling the laboratory generation of electromagnetic waves and leading to the discovery of radio decades later. More profoundly, they gave physicists a new way to picture the universe as a tapestry of interacting fields. In the early 20th century, Albert Einstein built directly on Maxwell's insights when he reformulated gravity. In Einstein's view, gravity is not a force acting at a distance, but the curvature of space-time itself, a vast field warped by mass and energy. Like electromagnetism, gravity propagates across cosmic distances, shaping the motion of stars, planets, and galaxies. Yet despite ruling our everyday lives, gravity is astonishingly weak. To produce noticeable gravitational effects, enormous masses are required. The curvature of space-time caused by a human body is vanishingly small. On the smallest scales, another force dominates, the strong nuclear force. Unlike gravity and electromagnetism, its reach is tiny, no farther than the width of a proton. But within that minuscule range, it is overwhelmingly powerful, binding quarks together into protons and neutrons and holding atomic nuclei intact. Then there is the weak nuclear force, weaker than all but gravity and confined to even shorter distances. It might seem insignificant, yet it is essential to our existence. By changing one type of quark into another, the weak force drives nuclear reactions inside stars, fueling fusion and enabling the creation of heavy elements. Without it, the sun would not shine, and the chemical building blocks of life would never form. Together, these four forces appear to govern everything we observe. But to understand what they truly are and how they emerged, physicists had to venture deeper into the strange quantum realm of virtual particles. On the shores of Cayuga Lake in upstate New York, Cornell University rests quietly. On late autumn evenings in the 1940s, a young associate professor named Richard Feynman would sit by the water, watching ripples form and fade as the wind swept across the lake. As he observed the surface patterns shifting under invisible influences, his mind turned to quantum electrodynamics. Feynman imagined the wind as a field, much like the electromagnetic fields described by Maxwell, spreading across the lake and shaping the waves. With enough information, he reasoned, one could reconstruct that field and trace it back to its source. But to truly understand the wind, it wasn't enough to study the field alone. One had to understand the particles of air carrying it, how they moved, how they interacted. Could electromagnetic fields be understood in the same way? Feynman was part of the quantum revolution that had unfolded over the previous 2 decades. Physicists had learned that light, long known as a wave, could also be described as discrete packets of energy called photons. Yet Maxwell had shown that light was fundamentally a wave in an electromagnetic field. Reconciling these views was a profound challenge. Feynman's solution was quantum electrodynamics, which treated the electromagnetic field as quantized and described interactions as exchanges of virtual particles. The photon, he showed, is the messenger of electromagnetism, not a solid particle like an air molecule, but a virtual entity that transfers energy and momentum between charged particles. Free photons appear as light and radiation. Even stranger, these virtual photons can briefly flicker into existence even in a perfect vacuum. In 1948, Dutch physicist Hendrik Casimir predicted that 2 mirrors placed close together in a vacuum would attract each other. The only possible cause was the pressure of virtual photons, more numerous outside the plates than between them. This Casimir effect revealed that even empty space is teeming with energy. Inspired by this success, physicists extended the idea of virtual messengers to other forces. The strong force is carried by gluons, particles that glue quarks together. The weak force is mediated by heavy W and Z bosons, whose large masses confine the force to tiny distances. Together, these discoveries formed the standard model of particle physics. Gravity remains the outlier. A hypothetical graviton has been proposed, but gravity's weakness and its incompatibility with quantum theory keep it beyond experimental reach. Despite these challenges, a remarkable pattern emerged. The forces that appear so different today may once have been unified. In 1979, Abdus Salam, Sheldon Glashow, and Steven Weinberg received the Nobel Prize for showing that the electromagnetic and weak forces are 2 aspects of a single electroweak force. At extremely high energies, they merge into one. Physicists suspect that at even higher energies, the strong force also joins this union, forming a grand unified force that existed shortly after the Big Bang. Though these energies are far beyond what the Large Hadron Collider can reach, they once filled the newborn universe. For a fleeting instant, all forces but gravity were one, and matter and antimatter transformed freely into one another. As the universe expanded and cooled, this symmetry shattered. Forces split apart, particles gained mass, and the cosmos settled into the structured form we recognize today. The Muon wobble anomaly may be a faint echo of that deeper unity, a crack in our current house of cards. Whether it heralds a new force or a deeper understanding of existing ones remains to be seen. But if history is any guide, the next great insight may already be waiting, just beyond the edge of what we think we know. So, what are your thoughts on today's topic? Make sure to like this video and subscribe to our channel HaiAstro so you won't miss any of our upcoming posts. Thanks for tuning in. See you next time.